Okay guys, I wanted to do another video here. This one is on the hydrolysis of salt solutions, and the goal is to be able to take a given salt and predict whether or not it will lead to an acidic, basic, or neutral solution. We'll have some calculations that we'll do in a second video, and for this third learning objective you can neglect that one. We're not going to have any assessments on that topic. The first thing we need to do is define what a hydrolysis reaction is. Hydrolysis refers to a reaction of an ion with water that will produce either hydronium, leading to an acidic solution, or hydroxide, which would give a basic solution. So here we have an example of each. Ammonium chloride is a strong electrolyte. It dissolves readily in water to give you ammonium cations and chloride anions. The chloride does not undergo any reaction with water. However, the ammonium is a fairly strong acid and is capable of donating a proton to water, which would give you ammonia and leave behind, or form rather, some hydronium. And so it's the formation of hydronium in this hydrolysis reaction that gives us an acidic solution. In this second example, we're looking at a sodium cyanide solution. Sodium cyanide readily dissolves in water to give you sodium and cyanide ions. The sodium does not react with water. However, the cyanide ion is a fairly strong base. It accepts a proton from water, which forms hydrocyanic acid, and leaves behind some hydroxide. I'll just point out a slight typo here. This should say cyanide, not cyanate. In the end, our salt solutions can either be weakly acidic, weakly basic, or neutral, and we need to be able to figure that out just given the salt's molecular or ionic formula. And so there's several cases here. In this first case, we'll look at the salt of a strong acid and a strong base, and the result is that a salt that's formed from a strong acid and a strong base is neutral. And so an example of that is sodium chloride. Sodium dissolves to form sodium and chloride ions. We associate sodium with sodium hydroxide and chloride with hydrochloric acid. Both of these are strong, and therefore neither of the ions will be capable of reacting with water. So sodium can't react with water, chloride can't react with water, no hydrolysis occurs, and therefore sodium chloride solutions are neutral. In this second rule, we'll change it up. This time we'll make the acid weak. So this will be a salt of a strong base and a weak acid. The result is that the electrolyte solution will be basic. So the sodium cyanide example fits that form. Again, you get sodium and cyanide ions. We associate sodium with the strong base sodium hydroxide. Therefore, sodium does not hydrolyze water. However, cyanide is associated with the weak acid hydrocyanic acid, and therefore cyanide is a fairly strong base, capable of hydrolyzing water, giving us hydroxide, making the solution basic. The next rule is the opposite. This time we'll have a salt of a weak base and a strong acid, and the result will be that the electrolyte solution is acidic. The ammonium chloride fits that form. It gives us ammonium and chloride ions. We associate chloride with hydrochloric acid, which is strong. Therefore, chloride cannot hydrolyze water. However, the ammonium is associated with the weak base ammonia, and so ammonium is a fairly strong acid capable of donating a proton to water, giving you some ammonia and some hydronium, which makes the solution acidic. In this last rule here, it's ambiguous. We can't tell whether or not the solution will be acidic or basic without doing a numerical comparison. And so a salt of a weak base and a weak acid can be either acidic or basic. And so we're looking at the ammonium formate electrolyte. It dissolves readily to give you ammonium and formate ions. We associate ammonium with the weak base ammonia. Therefore, this is a fairly strong acid that can hydrolyze water to give us hydronium. The formate we associate with the weak acid formic acid. Therefore, formate is a fairly strong base. It accepts a proton from water, giving us formic acid and leaving some hydroxide. And so the question is, which of these two reactions is going to be dominant? Are you going to have an excess of hydronium or an excess of hydroxide? And the answer depends on the value of the Ka for ammonium and the value of the Kb for formate. Whichever of these two ions has the larger equilibrium constant will determine whether there's more hydronium or more hydroxide at equilibrium. In this case, the Ka value for ammonium is larger than the Kb value for formate, and so we would expect a little bit more hydronium at equilibrium, and therefore the solution is going to be acidic. So this example is kind of like what you're going to have to do for the assessments. You can imagine problems where you're given a set of 5 salts, and the question is, which of these salts would give you an acidic solution, or which would give you a basic solution, or a neutral solution. And so you have to be able to pick apart the salt and determine whether or not you're going to have hydronium or hydroxide or neither at equilibrium. And so let me show you my process for doing that. I don't have the 4 rules memorized off the top of my head. You don't really need them. You just need to understand how hydrolysis works. So we'll start with potassium chloride. First thing you want to do is break that into ions, potassium ions and chloride ions. And then you want to ask yourself, do I associate either of these guys with a strong acid or strong base? The answer is yes. We associate potassium with potassium hydroxide. That's a strong base. Therefore, potassium will not hydrolyze water. For chloride, we associate this with hydrochloric acid, a strong acid on our list of strong acids, and so we don't expect chloride can hydrolyze water, and it doesn't. So for potassium chloride, since there's no hydrolysis occurring, we're going to have a neutral solution. For the sodium fluoride example, however, we don't associate we associate sodium with sodium hydroxide, a strong base, so there's no hydrolysis reaction occurring with sodium. However, fluoride is associated with the weak acid hydrofluoric acid. If you check back on the list of strong acid, hydrofluoric acid is not present. Therefore, the fluoride is a fairly strong base. It can accept protons from water, which will lead to hydroxide, and it's going to give you a basic solution. So sodium fluoride solutions are basic. We've already looked, I believe, at the ammonium cyanide. This is a case where both ammonium and cyanide can hydrolyze water. So the ammonium we associate with ammonia. That's a weak base. So ammonium is going to form some hydronium. Cyanide we associate with the weak acid hydrocyanic acid. So cyanide can hydrolyze water. It's going to give us some hydroxide. And based on the 2 reactions, we can't tell which of these is going to be dominant. We need some numbers to compare. So right now this is ambiguous, and we don't know the answer. For part D, potassium nitrate, neither of the ions are capable of hydrolyzing water. Again, potassium hydroxide, so no hydrolysis from potassium. Nitrate we associate with nitric acid, another strong acid, therefore no hydrolysis from nitrate, and so we're going to end up with a neutral solution for potassium nitrate. I've got several more examples to go through here. Potassium bromide, again, potassium hydroxide, strong base, no hydrolysis. Bromide, however, we associate bromine with hydrobromic acid, which is also strong, therefore no hydrolysis reaction from that one. So this again will be a neutral solution. For the case of sodium hydrogen carbonate, nothing coming from the sodium because we associate that with sodium hydroxide, so no hydrolysis from sodium. However, the hydrogen carbonate ion we associate with carbonic acid. You just add a proton to it. That's not on our list of strong acids. Therefore, the hydrogen carbonate is a strong enough base to hydrolyze water, which is going to give us some hydroxide. So we're going to have a slightly basic solution in our sodium hydrogen carbonate. The ammonium chloride. Ammonium is capable of hydrolyzing water to give you hydronium. However, the chloride cannot. Therefore, we're going to get a slightly acidic solution. In this example here, the sodium hydrogen phosphate, sodium, no hydrolysis reaction there. The hydrogen phosphate ion, we associate that with a dihydrogen phosphate ion, so you can just add a proton there. That's a weak acid, and therefore the hydrogen phosphate will be a fairly strong base. It can accept a proton from water, which would lead to hydroxide, and so you're going to have a slightly basic solution here. In these two examples, I'll work the first one. This is one of those ambiguous ones where they do give you the numbers that you need to solve the problem. And so here, looking at the sodium fluoride solution, both ammonium fluoride, so both ammonium and fluoride are capable of hydrolyzing water. What you need are the Ka value for ammonium and the Kb value for fluoride. However, if you go to your list of Ka values and try to find ammonium, you won't find it. You will, however, find the Kb value for ammonia listed under the Kb table. And so what you need to do is use the relationship between Ka and Kb for a conjugate acid-base pair and solve for the unknown Ka in terms of the known Kb value. So Ka would be equal to Kw divided by Kb. It gives you that value for ammonium. The same thing for fluoride. If you try to find the Kb value for fluoride in your list of Kb values, it won't be there. However, you will find its conjugate acid on the Ka table. And so you use the Ka-Kb relationship to find the Kb for the unknown conjugate base. You get that value. And then to determine whether or not the electrolyte is an acidic or basic solution, you have to compare these two numbers. And whichever one is larger means that that reaction will be slightly more dominant. In this case, the Ka for ammonium is larger than the Kb for fluoride, and so we're going to wind up with a slightly acidic solution. And I'm going to stop this video right here.